now, and he will teach us something on learning. So we want to learn something. Right?
Okay, thank you very much. Then this, yeah, I mean, like I haven't given like this type of the face-to-face talk quite a while, so it feels very odd, and then also makes me very nervous. So I may struggle quite a bit during my talk. So please help me by asking questions and so on. And what I'm going to tell you today is not quite on the topic of this discrete math and combinatorics, but potentially relates a little bit, because I'm going to talk a little bit. I mean, as you can see, there are SAT, SAT. I'm sure that all of you kind of heard about satisfiability problem of propositional logic before. So it had some connections with what you saw before. Also, there is also a connection with hopefully the Boolean functions that we study together. Okay. So I'm sure that many of you already heard about deep learning. I mean, even though you don't know what it is, you heard about lots of hypes about it, and then many people are excited about this. But then there are many challenges to overcome to make deep learning system to achieve what some people call general AI, or to do all sorts of things that people want to do. And one of the things is to kind of equip it so that it can do reasoning. So there are many famous examples of deep learning. They can recognize, they behave a bit like a perceptions of humans. They can recognize flowers, dogs, and cats, which are hard to do if you want to write a program. But on the other hand, what it doesn't do very well is to some form of reasoning. For instance, I mean, one example that you can see is the example of reasoning that you can see is a puzzle solving, like a Sudoku puzzle that you see on the screen. And people typically knows how to solve this kind of puzzles after, I mean, after getting to know a little bit about what the rules are. And also there are other branches of computer science, also related to combinatorics, which studies how we can come up with an algorithm to solve this type of problem. I mean, this Sudoku can actually be phrased as a graph coloring problem, so that we can use an algorithm to apply to this. Now, so people are aware of this type of limitation. There are many approaches to overcome this limitation in the deep learning community. And one of the approaches is to design a new type of neural nets, and that can do reasoning. So that can be what people call a layer, a component of a deep learning system. So it can be combined with the other components. But that component has a special feature, which is it's capable of doing the reasoning. So SATNet is an example which I'm gonna talk about. And then here's just something that you can do with the SATNet. So if we train the SATNet, one good thing about deep learning system is that we can learn. These systems is able to learn something from the data set. Okay. So if you learn a deep learning system well for this type of specific problem, you can do the following. You can take an image of Sudoku. It's not taking the symbolic representation of Sudoku. It's taking just an image of Sudoku, and it recognizes this. It converts image into some symbolic representation, and then it do invoke reasoning part of a deep learning system. That reasoning part knows how to fill in the blanks, and then it can produce the solution of the Sudoku. So that's a kind of combination of a perception and the reasoning at the same time. So what SATNet people want to do is to provide some components of a deep learning system that's capable of doing the reasoning and can also go very well with the other part of the deep learning system. I'm going to tell you more about SATNet, and then give you a sense about in which sense SATNet achieves its goal. Now, one important part of SATNet is that it can do learning. Okay, what does that mean in this context? Is that suppose I build SATNet some deep learning system that uses a SATNet as a component. Then what I can do is I can give lots of examples of image of Sudoku together with its solutions. Okay, I just give lots of pairs of image together with its solution. Solution may be a symbolic representation, and then I give a bunch of them. And then ideally, deep learning system with the SATNet should be able to figure out how to recognize the image. At the same time, it also should figure out what the rules of the Sudokus are, so that later when I give an image, it can convert that image into this board and then solve that puzzle. Okay.
Oh,
Yes.
so didn't they provide explicit rule of Sudoku?
No.
No.
No, so that's the purpose of this type of system. You just want to learn. So I mean, it can do reasoning, but at the same time, it can learn the rules of the Sudoku, rules of the puzzles from the examples. So that, yes.
Is it important that the solution is in a symbolic, given in a symbolic form, or
So
are there variants that
ideally, I mean, it can be an image in theory.
yeah.
Whether it works in practice, I'm not entirely sure.
Okay.
So there are many limitations about this SATNet, which I'm gonna cover, and then so it can perform extremely well in some cases, but not so well in other cases. Yes.
So by being able to do reasoning, you mean being able to solve symbolic logic? Or?
So I'm gonna tell you what it means.
Okay.
So essentially, what I'm gonna tell, what it means in this context is that it can solve optimization problem.
Mhm.
So there is a differentiable optimization solver. That's essentially what SATNet is. And then because it's differentiable, it can do learning by gradient descent. Okay. So then what we want to do, I mean, SATNet was a paper which was published before, but I mean, as like Ben pointed out, SATNet is not perfect. So here's the one puzzles that we tried, which is something generated from the Rubik's Cube. So we are not solving the Rubik's Cube, but what they did was that we performed some move on the solution of the Rubik's Cube. So we perturbed Rubik's Cube a little bit from the solution, and then we removed some of the blank colors of some of the places. Okay. So and then we ask some the puzzle is to fill in the colors of these removed blanks in the Rubik's Cube. So that is a bit maybe harder or maybe easier than Sudoku. So we are given a Rubik's Cube where some colors are missing. We fill in the color in such a way that it's solvable. It can reach to the solution of the Rubik's Cube. And then for this example, we gave lots of examples to the SATNet and asked it to learn the rules from the input-output example. So here we are not doing any perceptions. We are just giving symbolic input and output. And then we try to learn the rules of this type of, a bit related to maybe reconfiguration that Stain talked about. But so this type of rules. But then the SATNet actually learns something. So if it's this gradient descent algorithm, initially this test accuracy means that we give a new instance of the puzzle and ask SATNet to solve that puzzle. And initially it doesn't solve anything, but gradually it knows how to solve some of them. That means it learns something. But it is kind of reached about 50 to 56% of the accuracy, which means that it achieves something but not so great. So what we want to do is that we want to, in a sense, improve SATNet so that it can learn much better. Maybe the better means it can learn rules that we really care about, or it can, when it learns the rules, it performs much faster. So faster and more accurate, or more generalized better, that's what we want to achieve. So in fact, this is a chart that I've taken from my paper, and that if you apply our techniques, you can achieve something a bit higher, about 10% higher. It's complex. Okay, so then what's the idea? So I feel like if we want to achieve something, then we have to use something. So what are the ideas? The idea we have is that many of these type of rules have symmetries. So if you think about Sudoku, permuting numbers from 1 to 9, it's a preserved solution. If it's just something is a solution, if you permute the numbers, that's again to be a solution. Permuting the first 3 rows, last 3 columns, and so on, that preserve the solution. Also, although this is not always the case, sometimes, even though we don't know the rules, we know some of the symmetries. We know that some of the transformation that preserve the solution of the puzzle that we care about. So if we are in such a context, then we can ask for some domain expert to provide not rules because we don't know the rules, but provide some of the known symmetries about behind the rules. Then maybe we can use these symmetries to design a new type of SATNet that can learn a lot better. Maybe it's more data efficient, but it can generalize a bit better. So that's what we want to achieve, and I'm going to tell you about one kind of outcome of this research direction. Okay. So here's a plan of my talks. I'm going to tell you a little bit. I'm going to review SATNet a little bit so that so you can get some idea about what it is. Now I will tell you about our version of SATNet, which is we call SymSATNet, symmetry aware SATNet. And then this symmetry aware SATNet will assume that somebody provide the collection of symmetries as a permutation group. But we will, at the end, we're going to tell you about some algorithms that is designed to discover these symmetries automatically in certain cases. Okay, let me start with the review of SATNet. So here's a review of SATNet, a bit simplified. I mean, if we just want some phrase that characterizes SATNet, it's a differentiable optimizer that can learn an optimization objective from a data set. So it has a dual kind of routine. One is it's an optimizer, so you can call this optimizer solve optimization problem. But also it can do learning, which means that if you give a bunch of input-output examples, from that collection of input-output examples, it can learn what the optimization objective is. So it has this type of dual role. So what it does, more precisely, it's designed to solve the optimization problem of the form that you see on the screen. C is an n by n matrix. I mean, the V is also a matrix of size k times n. A good way to understand this matrix is you can view it as a n vectors, n column vectors. Okay, so matrix V. The best way to extend this is 1, 2. So it's n vectors, and then if you prefer, you can set k is equal to 1, which means that okay. There's another condition which is say that this vector, every variable vector, I mean vector with of this variable should be on the circle. So its norm should be equal to 1. So now consider the case where k is equal to 1. So if it's k is equal to 1, what this condition means that for each I, vi is either plus minus 1. So it's the kind of case that we studied in the Boolean functions reading group. Okay? Right. So say that in some simplified version, it goes like this. We are given n by n symmetric matrix C. And then this solver tried to find a minimizer V, or n k-dimensional vectors V, such that if you compute this guy, I mean that value is minimized. And then there's some condition, with the condition set all the norm of every vector has to be equal to 1. Okay. Right. So then but in the full version of this SATNet, the optimization problem solved by SATNet is n vectors, and some of them are regarded as an input, so some of them are fixed, and some of them are regarded as an output. Okay. So roughly speaking, the input VIs specify the numbers of the Sudoku puzzles, partially filled numbers, and then the output VIs correspond to the blanks of the Sudoku puzzle. Okay. Right. Okay. So then the interesting part of SATNet is that, as I said, it has a two-part. One part is a solver for this optimization problem. It doesn't achieve the global minimum, but it achieved the local minimum. And then it also have another routines that learns C from a bunch of collection of input-output examples. Okay.
So what is the meaning of this inner product?
So that inner product means this. So if we have C and D, the C, D are the n by n matrices. It's just inner product component-wise. So it's a summation of ij and okay. But now let's try to understand this a little bit better by considering the case where k is equal to 1. So if it's k is equal to 1, then this C transpose. Okay. Means the following. If k is equal to 1, all these column vectors are just Boolean variable, either +1 or -1. So, and then what this formula really say, I mean, is if you just unpack the definitions and you write the formula, what the formula really tells us is this one. For every Cij, we multiply by Vi and Vj. So in other words, and also, if Vi's are either plus minus 1, Vi square is always equal to 1. So that in a sense disappears. So this is really the second order, I mean the degree 2 multilinear polynomial which doesn't have any degree 1 terms. But if you assume some inputs, then we can also include the degree 1 term. So the point I want to make is that this is for Boolean case, this is just a almost degree 2 multilinear polynomial that again features in the Boolean function study. Okay. Right. So then let me just show you some instance of this. So what this means? This means if we have some problem, okay, then if we can express that problem, so think about only k is equal to 1 case. If we have some problem, if we can encode that problem using optimization over this type of degree 2 multilinear polynomial, then we can just use this solver to solve that type of problem. So one example that I want to give you is a graph coloring problem. So think about the graph coloring. It's a very simple problem. It's very easy. We have a complete graph K3. Then we have 3 colors. Okay. So then what we want, here's one way to encode this simple graph coloring problem into SATNet. I mean, it's stupid, but hopefully give you some idea about how the whole thing works. So for vertex 1, we introduce 3 Boolean variables, x1, x2, x3. Vertex 2, we introduce another 3 Boolean variable, y1, y2, y3, c1, c2, c3. And x1 is equal to 1, which means that this vertex has a color 1. x2 is equal to 1 means this vertex has a color 2, and so on. Okay. So then now I want to tell you we can actually encode the graph coloring problem using the polynomial of this form if we include the first order terms as well. Okay. So we write polynomial of this form, we ask its maximizer, that will give a coloring of this. Okay, how we do it? I mean, what are the constraints? The constraint is that adjacent. If x1 is equal to 1, z1 cannot be equal to 1, right? So the constraints say it's not the case. So one of them has to be false. So I will mix like a +1, -1, and then true and false. +1 for me means true, -1 means false to me. And then and so on. And so we have this type of constraint which say that essentially it's a proper coloring, and then the other constraints say for each of the vertex we cannot choose 2 colors. So there is something called x1. So one of them has to be false, and so on. Okay, so if you see a term of this type, that is really a 2CNF formula. It's a conjunctive numeral form where each clause has at most 2 literals, right? So if we have at most 2 literals, although I'm not going to tell you, I mean, we can encode these 2 literal terms as a polynomial of degree at most 2, because I mean this multiplication is really talking about interaction between 2 variables. So we can encode this type of constraint as a polynomial of degree 2. So if you just add all the polynomial that we obtained for the first, second, and so on, then we can obtain a polynomial of degree 2 that encodes this entire term, which means that if there are, say, I think, maybe
Don't we need some form saying that at least you have to have a true for x1 or x2 or
yeah. So I'm gonna have to add one more thing. So there are maybe suppose there are 20 terms of this kind. So then there are. I mean, I can define a polynomial f. So which is degree m1 degree 2, such that if all the constraints, these constraints are true, it will get a score 20. I mean 20 is some arbitrary number, it will get a score 20. If it violate any of the constraints, it will get deducted by 1. Okay. So if you violate one of the constraints, it's gonna get score 19. If you violate all the constraints, it's gonna get my score minus 20. So we can define a polynomial of degree 2 that has this type of property. Okay, so this number 20 that we can pick. But then once you pick this property, then we can kind of encode the things that Sang-il mentioned, because this constraint doesn't exclude the possibility that we are not using any colors for the vertex. So we add some extra term. We should add some constant alpha. So it's a constant of all the first order terms, where constant is reasonably small. So it's maybe 1 over 100, like a 0.01. So then if you add this term to this f, then here's what's going to happen. If we violate any of this term, any of these conjunctions, then we will get deducted by -1. So we are dead. We are not going to achieve the maximum. But if we meet all of these constraints, okay, so then now we move to this second criteria. This second criteria is how many of these terms we're gonna satisfy. Okay, and then because of this second criteria, well, if you maximize it, then only the proper coloring, which actually use some color for each vertex, will give us the solution of this graph coloring. So it's a bit kind of wordy, but you can see that graph coloring problem can be encoded as a maximization over this degree 2 multilinear polynomial. And then to cover this type of constant term, what we can do in the context of SATNet is to fix one of the vi to be all one, I mean there is some constant value, so that we can do this. Okay. Right. Okay, so this is, so then now how the optimizer works. I mean, you don't really need to understand the behavior of optimizer, but it's essentially a coordinate descent algorithm. Now, the one way to understand this design of this SATNet is that, I mean, this constraint ensures all the values of v's live in a compact set, and this function is a continuous function, so it should have a maximum and minimum. And then using some Lagrangian and so on, then you can show actually if you, so just don't worry about it. This algorithm to coordinate descent, it fixes all the coordinates except one variable, and you try to minimize the entire objective with respect to that specific variable, and you keep reiterate. And it turns out if you do what's written on the screen, that minimize the value of this function with respect to vi, the ith variables, and then if you keep doing so, it's guaranteed. I mean, this objective is keep decreasing, so it's guaranteed to reach the local minimum eventually. Yeah. So that's the algorithm, the optimization algorithm. But interesting bit about this optimization algorithm is that, so this optimization algorithm is a mapping. It given some part of v, which is this input part, then it produces the output part. Okay, so it's a mapping from the input v's to the output v's. And it turns out that is also differentiable. So we can use that fact to learn C. Okay, here's how it works. So to learn C, we have a collection of input-output pairs. So V1 in means some part of v's, which is given as an input, V out means that the remaining part which is given as an output. And that's the part we want our optimizer to find. Okay. And here's one simple way to learn C from this set of training set or learning set. One thing you can do is we'll compute the errors of the current value of C with respect to this input-output pairs. So this is a computing set, applying SATNet to V in of ith inputs. Then you get output and you compare with the output and then just measure the distance. And then we try to minimize the distance. So it actually should be minus instead of plus. So we take a derivative which points the direction of C, which minimizes this difference. And we just keep following this direction, which is essentially here descending algorithm. And this is the algorithm that's employed in the SATNet to learn the parameter C from a data set. So it computes this error for the training set, each training example, and then it compute its derivative and follow the derivative. But for this to really work, we should have some efficient way to compute the derivative. And actually, SATNet has an efficient way to compute the derivative, so that's the key feature of the SATNet. Okay. Right. So does that? I mean, are you following me so far, or more? Yes.
So as I understand so far, so that V transpose V means that there are some kind of interactions between for example, in your example, there are interactions like xi and yi, but how about if there are 3 or more degrees?
So if you have a 3 or more interaction among the 3 variables, then you can there is one known result in discrete optimization, which said if for so-called 3 set can be encoded as a 2 max set. So by introducing some extra variables, and then if you formulate the problem as an optimization problem, you can simulate the interaction among the 3 variables. So if there is a proper interaction, your score of optimization goes above the bar. If the 3 variables interact badly, then your score can become below the bar. So 2 set is now, it's much easier than 3 set, but 2 max set, optimization or version of this 2 max set, to satisfiability is actually as strong as this. It's an NP hard problem. Okay, so now let me move on to our result, which is about symmetry-aware SATNet. So now in this context, what do you mean by symmetries? So here's what we mean by symmetry. So intuitively, symmetry means that solution doesn't really change. So it's just a collection of transformation on the solution, which doesn't change that something is a solution. Okay. But in this context of a SATNet, it can be viewed as some transformation on the input, which preserve the value of the objective function, because the objective function is something that determines the solution. So if your transformation doesn't really change the objective functions, then that can be regarded as a symmetry of the specific problem. Okay. So now, but then we are only thinking about the particular symmetries that can be determined by a permutation group G on N. So what that means is the symmetry that we care about is going to be the kind of renaming or rearrangement of the variables. Okay. So one symmetry may be try to replace x1 by y1, x2 by y2, x3 by y3, and then the z1, z2, z3, it doesn't do anything. But then if you do so, then some solution of this graph coloring will remain to be a graph coloring. Okay. So that's what's going on here. So we said that group G is a permutation group on N, and then we say that this group G captures the symmetries of the optimization problem of SATNet if the following condition is true. So for any permutation on G, then this is Vg, just the V sigma, just means that we are going to obtain the matrix like this, but The first guy is, I think, it's either sigma minus 1 or sigma minus 1. So it's a rearrangement of the order of the variables. So we apply this rearrangement on V on this side as well as the other side. And then we are saying this this G capture symmetries where if this rearrangement doesn't change optimization objective. So from the perspective of the optimization, I mean this V and V sigma, they are essentially the same things. Okay. So that I think intuitively correspond to the symmetries of the problem. And in fact, for Sudoku, if you express Sudoku problem in this way, I mean Sudoku is a graph coloring, can be seen as a graph coloring problem, so it can be done something like this way or some other way. But it has the symmetries. The symmetry is of this form. This S9 at the end just corresponds to changing the numbers from 1 to 9. And this with product of S3 means that changing the first rows and the first columns, the rows in a nested way, this corresponds to the changing the columns in a nested way. Okay, so the group this G captured the symmetry of the Sudoku. Okay, so now, so this intuitively corresponds to the symmetry of a given problem. But it's not really good for us because what we want is that we somehow want to exploit this symmetry to make our learning problem a bit easier. So what's our learning problem? Learning problem is given set of a collection of input-output examples. We want to learn C that maps inputs to the output via this optimization. And here's a very simple observation that will make this possible. So here are two key lemmas. The one key lemma is that actually this symmetric condition can be phrased in terms of so-called G equivariance. So for every, I mean, if this equality is true for every sigma in the group G, and for every vector V, if this C is so-called G equivariant, which means this condition. You say that for every permutation sigma, consider its permutation matrix. So we compose C with a permutation matrix. That is the same as the permutation matrix composed with C. So permutation matrix and C commute. So that's what this equivariance condition say. And these two things are equal. I mean, not two things are equivalent. The one below implies the one above. Okay. Then, I mean, let me just write down this condition here. So the condition is if you have a viewing it as a diagram, it might make it a bit easier. So this is C is an n by n matrix. That's a linear transformation that goes from the Rn to Rn, the same thing. Then sigma, if you view it as a permutation matrix, that's also a linear transformation from here. So the equivariance condition essentially means that this commutative diagram is true for every sigma. Okay. So in the form, the intuitively what it means is C doesn't really depend on the, I mean C only works on the, in some sense, equivalence clause induced by this permutation. Yeah. Right. But then, I mean the proof is not very hard. If you, I guess it's I mean, the only purpose, if I show the proof, the only purpose is just to help you to understand this theorem, but this statement. But I guess it's clear what the statement means, right? So, and then the other interesting bit is that now suppose we collect, actually it becomes equivalent only if k is equal to n. I mean, again, if I just make some link to what we have been doing in the Boolean function reading groups, we talked about some similar kind of properties of the Boolean functions. So potentially this G equivariance and so on might be analyzed in terms of what people did, the kind of things we studied in the Boolean function. Yeah. Also, I mean, this is C. If I just make another connection with the Boolean function stuff, this is C is really a coefficient of these second order terms. So it's really what in the Boolean function context called Fourier spectrum for Vi, Vj, right? So there are some connections. whether it really leads to something interesting, I'm not entirely sure. But something to explore. But the second lemma is that now if suppose we only collect this type of a C, which is this G equivariant. So that's what this is E of G means. All the matrix, let's see, it's symmetric, and the symmetric is equivariant, and it turns out this collection of these matrices form a subvector space. It forms a vector space, and this is in a subvector space of it's a symmetric matrix on Rn times n, and it's not very hard. We can just show this. That's the case. But one interesting bit about this is that the dimension of this vector space is usually much smaller than the dimension of this symmetric matrices on in Rn square. I mean, symmetric matrices on R square, their dimension is dimension of this guy is n times n plus 1 divided by 2. But the equivariance matrices, I mean, it's much smaller. For in the context of for Sudoku example, the dimension of this equivariance space is 18. But the dimension of all the symmetric matrices is 729 square. So it's much smaller. So what that means? That means if we somehow can, suppose we don't know C, but we know that C lives in this equivariant space of this E of G. So then if we can kind of parameterize C in terms of some basis of this equivariant space, then because the dimension is much smaller there, it's really essentially, in the case of Sudoku, it works on 18 parameters instead of 729 square parameters. Fewer parameter usually means learning is easier and it generalizes better. So that's what actually we did. So SymSATNet is essentially a SATNet, the same as before, except that the parameter matrix C now is guaranteed to live in this equivariant space, E of G. So SymSATNet assumes the group of symmetries is given, although C is not given. So it knows that the C, unknown C, which we want to learn from examples, lives in this space of the equivariance, the n by n symmetric matrices. Okay. Now, what SymSATNet does is that given G, so if G is some specific form, there's an automatic way to generate each basis. We generate each basis, and then we parameterize C by essentially linear combination of these these basis matrices. So as I said before, the number of the dimension of equivariant space, which corresponds to D in this case, is much smaller than this dimension of this sim Rn square. So that means that SymSATNet can work on the much fewer parameters than the original SATNet. Does it really work well? And here's some numbers from experiments. So this is we apply, essentially all the routines of SATNet, like optimizers, as well as the part that compute the derivative, they can all be carried out into this SymSATNet context. So we use this SymSATNet to learn the rules of Sudoku and the Rubik's Cube. And these are the numbers that we got. So this is the so-called test accuracy. We run these rules from using SymSATNet as well as SATNet, and then we test whether the learned rules are reasonable by applying these optimizers on a new puzzle instances. And then Sudoku case, if we just apply the SATNet without any extra auxiliary variable, it solved 88% of the new problem instances. With 300 auxiliary variables, its accuracy goes up to 98%. But for SymSATNet, the accuracy without any extra auxiliary variable, it goes up to 99%. I mean, which is not very surprising. We give a lot more information here. Number of parameters to learn is, I mean, it is much smaller, so it should learn much better. Cube case, yes.
What is the auxiliary variable?
So if for SATNet case, we have 729 variables, but auxiliary variable just means that we add something extra. So in addition to this n, we add, I think, 300 more.
So it's easier to learn if you have just 300 things you don't care, 300 extra variables. You don't care
For
about.
Sudoku case, SATNet, that was the case, but for cube, it's not.
Yeah.
So it makes things more expensive, so that we can see the time blow up by 2 times. But then in the case of Sudoku, it helps quite a bit. In the case of cube, it didn't. The accuracy doesn't really improve at all. So it really depends on the problem. I think if you add some, ideally, if you add some extra variables, and if you use these extra variables well, then you can solve the problem. But I think that's asking too much. We are really asking SATNet to discover problem reductions from 3 set into 2 max set. That's going to be very, very hard. So it's for some cases it works well, but some other cases it doesn't work.
So what does symmetric SATNet here means? Are they given? Do we tell them what's this G?
That's right. We for symmetric SATNet, we tell them what G is, and then from the G, it compute its basis, and then we reparameterize this C in terms of this basis.
So for different problems, we have to tell them beforehand what are the corresponding.
Indeed. Right. So that's actually my next slide. So then what are the caveats? The caveat is that we have to give these symmetries the group G. It's sometimes easy, but sometimes it's very hard. For Rubik's cube case, it's more complicated. It has a risk products and so on. And actually, it's not very easy sometimes. It's maybe, yes?
Isn't it sometimes easier just to tell, like, this is the thing you have to solve, and then it has 100% accuracy, and it's
Sorry?
much, like in the case of the Rubik, the Sudoku, like maybe it's even easier to give them just like you have to solve this instead of giving them the group of symmetries. Well, if you give the problem, it can solve it
That's
with
right.
100%.
So sometimes, I mean, but if you, for the symmetries, if you give not all the symmetries, but some symmetries, it still helps. So the symmetries are more like a prior information that you can provide. So even though you don't know the rules of Sudoku, you may just say, okay, permuting number from 1 to 9 doesn't really change the solution. So that much can also be incorporated. Yeah. But I'm going to tell you how to overcome this issue a little bit. So that's the last part of my talk, how we can deal with this limitation which requires somebody has to provide the symmetries. So here's it's very difficult. I mean, learning, you have to make some assumptions, otherwise you can't do anything. So here's the mixture of empirical assumption and some properties, some mathematical property. The first property is that actually the G equivalence can be, if you just unpack the definition says the following. It says that for every sigma in G and index ij, this is C of sigma I, sigma j has to be equal to C of ij. If you view C as an adjacency matrix of a graph, it really means sigma is an isomorphism, right? Because between ij, if there's an edge, if and only if sigma I, sigma j, there should be an edge. That's really a graph isomorphism. But in terms of the values of the matrix, what this condition tells us is that there are a bunch of groups, there are a bunch of clusters. Some cluster, they all have the same value, because it's all happening in the same G, same C. So there are a bunch of entries in C, they have the same value. A bunch of other entries in C, they have the same value, and so on. So equivariant matrices have this type of cluster. So if you visualize matrix C, then there are one big part which have the same value. If it's equivariant, there are also this part which have the same value. And this part, and maybe this part, they have the same value and so on. Okay. If it's a G equivariant. Okay. So this is a pattern that we can that follows from this definition. Okay. Then I will call it is a clustering pattern. And then here's a second, which is now, but we don't know that this equivariance thing. But what happened is that during the early phase of the training with the SATNet, okay, so SATNet is learning this matrix C from an examples. But when it learned C in the early phase, this type of symmetries actually, this grouping or clustering pattern actually emerged during the training. So this is the example that we took in when we apply SATNet in the Rubik's Cube problem, maybe in the so-called 20th epoch of the learning this parameter C. So it's not completed learning. It's a very reasonably like an early phase of the learning. But then, although it's not very easy, you can see that this color represent numbers. So you can see the similar colors appear in multiple different places, right? So I said the equivariance condition intuitively means many entries are the same. And in this picture, you can see that there are like many entries have the similar values. So what does that mean? If now take this C.
Sorry, I think you made me feel like I'm colorblind. Are you saying the colors representing values?
Yes.
I see just all blue. All teal
Sorry.
colors.
But this is a degree of blues. So there are some blues which are the same. There are some blues which are,
Okay.
but what I'm telling you is that in the matrix C, which is an n by n matrix, if you look at each entries, you can detect actually many equal values, many similar values. So there's a group 1 with many equal values, group 2 with many equal values, and so on. That's a good indication that like a equivariance condition is kind of satisfied in a weak sense. Approximately, because equivariance means this type of grouping should emerge. So that's what we used in our algorithm. So our algorithm works like this. Our algorithm or heuristic, whatever you call it, this is how it works. What it does is that it first, given a data training or learn data set from which we want to learn parameter C, we first run this SATNet, which doesn't require specification of symmetries at all, a few times. Okay. Then we take the snapshot C at some early phase of the training. Now we freeze it, and then from this C, by looking at this what I call clustering patterns, which values are the similar, we try to find a group and a permutation such that if you form this type of permutation group, the permutation group captures the symmetries inside this matrix C well. Okay. I'm gonna tell you all these things one by one. I have 10 minutes, but I'm almost done. So this, let me just go to the condition 2 and 3. Condition 2 means that this permutation group that we formed, and this E of this permutation group means equivariance space of n by n symmetric matrix. Now, that because it's a vector space, we can project any matrix into this subspace. Okay. So we project matrix C to this subspace, and then this is just original C, and we measure the distance. So if that distance is large, that means projection changes C a lot. So that means that it's actually C is very unlikely to be equivariant with respect to this group. Okay. So we measure the distance after the projection. If it's already equivariant, the projection will not do anything. So this number is equal to 0. So we just one of the conditions we want to satisfy is that this distance should be bounded by a certain threshold lambda. So projections doesn't really change much. So C is already reasonably close to equivariance space. And okay, so that's the one of the condition. The third condition is, because the whole reason we do this is to obtain efficient SymSATNet. So we want this group the dimension of the group to be small. Okay. And the other part is that we are not looking for any G. We are looking for G that can be expressed by a grammar. Okay. This I is just the trivial group which only have a unit. The Z is a cyclic group. S is just the group of all the permutations. Then we are thinking about this construction of the groups. One is for the direct sum, direct product, and wreath products, and so on. Because these are the kind of constructions that you use to capture symmetries of many interesting puzzles. Okay. Okay, so the one approach to achieve this is really try all the possibility of G and sigma. I mean, there are only finitely many possibilities. And then compute this number 2, just filter out G and sigma that satisfy number 2. And then among those, we find the one that has the minimum dimension. But the problem with that approach is that it's not efficient. So what we do instead is we look at some common patterns that arises of the equivariant matrix with respect to this direct sum group, direct product group, and with products group. And we can analyze this because we know how to compute its basis. So we know how to compute the basis of the equivariant matrices with respect to direct sum group. Also, we know how to compute the basis of the equivariance matrices with respect to direct products and so on. So based on that information, we know that certain patterns should be true because every matrix should be a linear combination of these base matrices. So here's I think the best way to actually show you a picture. I'm sorry, may or also not entirely clear.
No, I can do it.
Okay. So this is the input matrix of SymFine. Then here's one of the things it does. Okay, what it does is that it tries to rearrange rows and columns by using the same permutation sigma. So you try to find some permutation sigma such that it can be arranged the matrix on the other side, on the left hand side. You see the matrix on the left hand side, it's a block matrix, and then each of the off diagonal blocks are all constant matrices. Like this one is a constant matrix, and so on. Diagonal blocks are matrix but will have some pattern which we call cyclic. So if you take the matrix over here, the diagonals are all red, and then the blue is also go down and so on. So it has certain patterns, and it turns out this is a pattern. Some of these patterns are actually true all the time. Some of the patterns are more empirical, but then this is a kind of pattern that emerged in the equivariant matrices with respect to the direct sum group. So we in a sense transform it. Our search is kind of exploit this type of pattern that exists. And then here's one more. For the direct products, in order to find the direct product group, what it uses is the following information. If C is if it's equivariant with respect to the direct product group, then it should be a linear combination of so-called canonical products of two matrices A and B. So roughly it should have some shape of this form. And then the question becomes how we can find A and B. Then we can do some kind of what they call reshaping and then apply the singular value decomposition of the reshaped version, then we can find this. So it's unclear. I'm sure that it's not very clear what's going on. But the point I want to make it is that there are patterns. If something is equivariant with respect to direct sum group, it should have a certain pattern. If it's equivariant with respect to direct product group, it should have certain patterns and so on. And then we are exploiting these patterns to make our search more efficient. And does it work? And if you apply it to Sudoku, it works perfectly. Our algorithm always finds that with 10 random trials and with the random seed, it always finds the right groups. So you really like that the symmetries may be easy. So during the SymSATNet, this symmetry emerged. For Rubik's Cube, it's not. The symmetry is more complex. Target symmetry looks like this. And then what's found is almost all the other parts are found except the part that's marked as red. For that part, the found symmetries are only approximate. Okay. But if we apply the SymSATNet with this found symmetry, we can achieve the similar kind of high performance. So this red line is the one that that combined this symmetric finding stuff and the SymSATNet. So what it does is that at a certain point of the run of SATNet, it uses its parameter matrix C, it finds symmetries, and it projects this C to this equivariant matrix space, and then continue with the SymSATNet. Okay, so then you can see if you go somewhere, because the initially it's same as SATNet, But then when this symmetry finding happens and projection happens, it just go up to actual convergence immediately. Yes?
On the top one, it looks like it goes above the one where you give the group.
Oh.
Oh,
Like on the Sudoku chart.
The
green
green
curve,
curve,
some
some area
uncertainty
goes
region.
above.
Well,
so I
let's-
think
let's-
what happened is we tried maybe I think 4 or 5 times, and then compute the confidence interval, so using some formula, and then the formula gives us some number higher than 1. So we just I mean it doesn't really show our numbers. It's more like among using 5 runs, you compute the standard deviation or something. Then yeah. So that's why the number can go up. So, but you're right. I mean, it shouldn't go above 1, because 1 means like 100%. But it's just some calculation. The formula that you use doesn't really know number 1 is an upper bound, so it can go up the number.
So that shows some range multiple
Yeah,
of
yeah.
some
So
standard
that's
deviation.
right. So if the standard deviation is really large, so if the standard deviation covers, for instance, this red and blue line, that means the conclusion is inconclusive. Sometimes it performs well, sometimes it doesn't perform well. So it's inconclusive. Some meaningful conclusion means the standard deviation, this region shouldn't overlap. Okay. Okay, so that's actually the end of my talk. So just finish. Yes.
Thank you. Any questions?
I'm wondering, since at some point you also mentioned like, oh, there are only like, it's a finite group, so it's just a finite list, but these can be big, since if you have, for example, the graph coloring problem, like if you have like 100 nodes, then it's probably still slow, I guess.
Right. Yeah. So if we want to try like all the groups, then I don't think it's gonna work. There are too many. So actually, one of the previous implementation tried do something like this. At some point, it do the enumerative, the exhaustive enumeration, and it doesn't really work. I mean, it was too inefficient. So, because like the whole reason to do this is to get learn better. Also, when we want our algorithm to run faster. So if we take forever, then it's not usable.
But it can solve some large graph coloring problems, or
So we haven't tried it, but the Sudoku is reasonably large graph coloring, but it's not like 1 million nodes or something. So I think the Sangil pointed out to me that for graph coloring, so what's the other problem in this context for the graph coloring? I mean, we really have a lot of colorings of an unknown graph. We want to find the graph. So that's really the problem we are solving here using Sudoku. I mean, this guy is solving. This guy is more general, but that's what this one is solving using gradient descent. And for that specific problem, there is a study about learning graphs from colorings. So by Vigoda and others. So one kind of possible question is how does it relate? Very unrelated, perhaps, but yeah. Yes.
First, maybe I missed some kind of details, but is there any number of the data sets to train you recommended?
So the data set, this original developer of SATNet, they made the data set available. So, but let me just mention 2 things. If we when we use this data set for the cube problem, we generate our data set, but so it's not just kind of data set taken from some existing Sudoku book. It's more like a synthetically generated data set. But we are using one of the data set is something generated by original authors of Sudoku. And let me mention one more thing. We tried to generate data set of Sudoku using set solver, but then this Ungeer, one of the co-authors of this paper, told me, which may or may not still be true, might or might not be true for the current version we have. What Ungeer told me, in the early phase of our work, is that if you use the data set that it consists of very hard Sudoku problem, then the SATNet doesn't really work well. So his criteria was hardness was that if you, while solving the Sudoku, if you need to do backtracking once, that's harder than instance which doesn't require backtracking. If you need to do backtracking twice, it's even harder and so on. So if he created hard examples and tried to train SATNet with this hard example, he said it doesn't really learn anything. So it may be, ideally it can learn something, but the story becomes, I think, much more proper theoretical understanding about what's really going on is highly non-trivial. Yeah.
What does it mean for an instance to require backtracking?
If you solve Sudoku, so one way to solve Sudoku is just look at blank and then come up with all the constraints, and that constraint tells you actually that blank should have number 3.
I see.
So that's an easy instance. Hard instance is that there are 2 options, like it can be 3 or 4, but then if you put 3, if you keep doing this again, at some point you realize actually you got stuck, so you have to backtrack, and then instead of 3 you have to put 4. So the stat solver, when you solve this type of problem, it performs something like this. So there are something called decisions, which is like a choosing, and there's also backtracking. Yes?
So if I understood you correctly, you do this symmetry guessing step like once, right?
Yeah, that's right.
Could there be something to be gained from after doing this and learning some more, like trying to re-guess?
So
like
I
maybe
think
randomly perturb?
so I can tell you 2 things. One is it's very empirical. This is lots of heuristics. But for our examples, as you can see that at one go, it performs really well.
Yeah.
So there wasn't no reason to think about it.
Right.
Other things we tried was that instead of taking the C in the early phase of the training, we tried to take C in a bit later phase of the training. And then what my student told me was that, my co-author told me was that it doesn't perform very well. Because SATNet while SATNet gets trained, to the learning, in the later phase, it looks like it's overfit to the specific data set. So symmetry somehow disappears. So that I also found interesting. I don't know whether this is all very empirical and also with respect to 2 instances, but then this symmetries appears before you do overfit. If that's really the general pattern, I found it's quite interesting. Yes.
So you point that the dimension of the vector space is much smaller than the symmetric
Yes.
case. So is there some theoretical lemma which guarantee that if we have this amount of generator of the G, then the dimension of this space is smaller than something else?
So there are, I don't know about that kind of lemma, but there is some lemma which say that if I think about the group which is built by the direct products, then if the dimension of equivariant matrices with respect to the first group, if I know the dimension of matrices with respect to the second group, that may tell us what's the dimension of the matrix, this equivariant matrix with respect to the direct sum or direct product groups. So there is some kind of inductive way to construct a basis. Okay. And actually understanding this basis is crucial because that's closely related to the pattern that I mentioned to you. Yes?
Is this problem also related to abstraction and reasoning? Like, for example, seeing 3 or 4 examples and find what kind of pattern inside and try to infer?
Yeah, that's right. Generally, finding the symmetry can be phrased as another kind of learning problem, and to do some generalization. So there may be some. If we approach it more properly, there may be some way to show something about this more formally and more systematically.
Any other questions? Good. If not, let's thank the speaker again.